Hey, welcome back to Fat Mama Physics! In this video, we are starting a new unit called Similarity and Scale Factor. In other words, geometric proportions. So, lots of visualizations, very applicable because you might have seen this, you see this all the time. You see scale factors, you see things that scale up, scale down. And I did mention that at the very beginning of every video I will introduce a board game, but after this board game I have something else I really want to show you. But because of the lag on the computer, which I don't know if it's going to transfer very well for the video, I will just show it to you and maybe you can play with it yourself. So the game that I have, and it's not really my favorite game. I don't really play it, but it's a very difficult to find a particular game for this lesson, which is scale diagrams and enlargements. Enlargements only. You can imagine that if we're talking about reductions, almost every board game you can probably relate it to how it's like a scale factor but a reduced scale. So enlargements is trickier because I have to find a board game that blows up reality by a certain amount of like in terms of the scale. But I found one that just very plain and simple. It's called Subatomic. Take a look at the game board. You can see better lighting, maybe. Okay. All right, so there's the game. It's called Subatomic, and you probably know bits of your atom from science class, maybe even last year in Science 8, potentially. So this is a game that talks a bit about what is a little bit smaller than your atoms, talking about your quarks, which maybe you might have a chance to discuss last year. We know very well that atoms, quarks, are much smaller in real life than this board game, for example, the size of this board game, and of course the components of this board game as well. So I consider this as a scale up. You are blowing something small to something very big in size. It's this board game, in fact, the reason why I don't like it as much is because it's an educational game for sure. It does a decent job. And educational games, I've designed education games before. There's one that is published, but the common difficulty of designing education games is very hard to make the game not only relevant to learning the learning objectives, but also making it fun and connecting the mechanics of the game with what you're trying to teach. So this kind of a game is called a set collection. Essentially, what you're trying to do is you're trying to collect a bunch of quarks to make protons and neutrons. So, for example, if you want to make a proton, you need 2 up quarks and 1 down quark. So these cards. And after you collect the set, you can trade them in for bigger subatomic particles. So in this case, I would be able to get myself a proton, which is somewhere here, okay? So then I trade in for a proton. It's like currency. It's like you get a proton, you can buy better things or something. And you're like, what? How can you buy things with subatomic particles? And that's where these little things come in, which is the next step. These guys over here, these are elements. For example, I have lithium over here. Okay, if you can't see lithium, let's use an easier one. Helium. Helium one is a smaller nucleus structure, and you can see I need 2 protons, 2 neutrons, and 2 electrons to make a helium atom. So as I am putting my quarks together, I need to collect 2 protons, 2 neutrons, and 2 electrons. And you're wondering, how do I make neutrons again? I know some of you don't care, but those of you who do care, your neutron is 2 down quarks and 1 up quark. Okay, so I have all these in my starter deck, so I can always I cycle through them. And to make an electron, it's using these 2 photons. But the game itself, here I'll show you the cards for all of these. Here's the neutron. Okay, there's a neutron. It actually tells you on the bottom how to make it. Here's an electron. There it is. So the game tries to match the science with the mechanics, but of course, we all leaves a little bit of details up. For example, in fact, you need, if you put two photons together, you create an electron-positron pair. On the other side, if you take an electron and a positron, which is its antiparticle, you get something called pair. You get annihilation of the pair and producing energy, which is photon particles, or gamma rays, essentially light. So you take photons, you combine them into to make electrons, and then you get some protons and neutrons. You put them together, collect these different elements, and of course they're going to score you points in the game. So it's kind of like it's a little bit deck building. It's a bit set collection. It's not anything spectacular. I mean, it's kind of like you do what you got to do to do what you got to do. So. It's the educational part is there, but I don't find it necessarily fun, so that's why we don't play it. But I do find it really awesome that this game is actually available, because I've always wanted to design a similar game to teach this concept in grade 8 science, but it's very difficult with a class. You need a game that is the rules in this game are too complex for a classroom setting. It's not as it's also not very good for everybody in the class engaging together, and also it's not very it's not. If I reduce the game to say something that's simpler, it also loses the fun factor a little bit. But it's hard to say, it's hard to say. But it's in the working, and I appreciate the fact that the game is available, so I don't know, maybe in the future I'll find a way to change it up. That's a scale factor when we have to enlarge something small to make it big. That's what I have here. So give me a second to put every parts of the game away. Okay, so I am back, and I promise I want to show you this cool site. It's called scaleofuniverse.com, scaleofuniverse.com. You could type this in, or I typed into Google Scale of the Universe, and I think there's also a part 2 or a better version or something. You just have to search it on Google. And I guess this is this one. It says the Scale of the Universe too, but anyway. So we're gonna start. I think there's some music, but we'll take a look at it and see what it gives us. Okay, so this is a human. This is a flower of whatever it's called. I don't really care. There's a beach ball. A dodo bird. Anyways, so what this is, it's 10 to the power of 0, and learning exponent laws and whatnot, you know that this is just 1. And what scale is this? This is measured in meters. So at 1 meter, this is roughly what you see. What we can do is we can zoom in and zoom out to look at how things scale up and down. So I don't know, which way would you like to go? Do you like to go in or go out? Let's go in first, a little bit. So I can just scroll and notice this is 10 to the negative 0.8. So I'm going to go a little bit further. So that gives us, a little too much. Just a tad bit. No, I just zoomed out. Sorry, the opposite way. So about 10 to the power of negative 1 means 1 over 10. That's about 10 centimeters. So these things are about 10 centimeters here that you see. So maybe I use this. Maybe this is better. Okay. What's that? That's an approximate size of this viewport. Oh, cute. Oh, yeah. It is roughly 10 centimeters on the screen, hey? Okay, we can keep going in. Matchstick, chicken egg, shrew. So this is a square inch. Ooh, glass marble. So we're getting to 10 to the negative 2, which is 1 centimeter. This is about 1 centimeter now. Oh, it even tells you on the big screen. So this is a millimeter. That's 10 to the negative 3, 1 over 1,000. Oh, an LCD pixel, grain of sand, thickness of paper. So the scale here, it is much smaller. We're seeing things that are blown up into our face, but in reality are much smaller than what they are. You might notice some of these guys, white blood cell, chloroplast, mitochondria. You learned this last year in science. So this is, what scale is this? This is getting to the micrometer, but we're seeing this up big. Ultraviolet light, mimivirus. I wonder if they put coronavirus on this thing. Bacterial, that's the largest virus. Yeah, viruses tend to be much smaller than this. HIV virus, some of you might have learned that last year. Hepatitis B virus. So these are very tiny. Resistor gate, very interesting. Phospholipid bilayer, DNA. Gonna learn that later than science, hopefully. Phospholipids, oh yeah. Carbon nanotube, very cool stuff. Oh, nanometers. So you might heard of nanotechnology. So this is how small they are, and it's getting to the atoms. Okay, hydrogen, helium atom, 10 to the negative 10. So that is 1 over 1 and 10 zeros. Gamma ray. We just talked about gamma ray earlier. That picometer, 10 to the negative. Oh, let's take a look at the number. Ooh, the number. Here. So notice this 10 to the power negative 12. So the negative exponent is telling you a very tiny number. So in terms of a decimal, you can count the number of decimal places, or number of zeros here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Shoot, I can't count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros, okay? 12 zeros for negative 12. So let's keep going. Is it this way? Yes. Alright, I'm just gonna go all the way to the end. Ooh. I think you will have a much better time playing with this than I am. So bam, top quark. Oh, we just saw the quark. Oh, everything is zooming way past us. We're just going, scaling down to the tiniest thing. What is the tiniest thing? A Planck length. Ooh, a Planck length. So, a Planck length. How do I put that inside in kind of language that you might know what it is? Kind of has to do with how, has to do with light and how it relates to energy. I think that's the only way we can put it into a simple way of it's kind of like almost like a ratio, but it's not. Okay, so anyways, it's very complex stuff. So that's kind of the idea. 10 to the negative 35. So that's one. It's like 1 and pretty much 35 zeros, and of course there's a decimal in there. So let's go back to the human. Go back to human size, and then you can keep going and zoom out. So instead of becoming very small, we're gonna go very big. So we're gonna scale up, which is enlarging things. Or actually, we just enlarge things using what you just saw, okay? So that's called enlargement. Now, notice I'm going out. I'm pulling out. And, which means, zooming out means I am going to be seeing things that are much bigger in reality, but smaller on my paper. Okay? That's gonna be the next lesson. So I'm gonna save this for next time. So I'm gonna turn off the music now, and, it took a while to load this page, so maybe I'll just keep it on. Okay, so let's go to here. Scale diagrams and enlargements. Whew, that took a while. But guess what? If you want to play with that app, you just go online and do it yourself. I know I probably zoomed out too quickly. Oh, you can actually press things. Like I can press on this guy and you can read it about dinosaurs. Some of you might love dinosaurs. If you had Mr. Bond last year, you would love to talk about dinosaurs. Okay, sorry about that. Let's continue with what we want to do today, which is scale diagrams and enlargements. In this part of this video, I'm just going to give you the quick recap, maybe show an example. Next video, we are going to do more examples. Let's go. Okay, so here we have an example of a tiny mosquito. in reality, they're very tiny. We want to blow it up, so maybe on a piece of paper we can talk about certain structures. Just like maybe if you want to see a diagram of the coronavirus, COVID-19, they're very tiny, but if we want to draw on a piece of paper, they are scaled up. That's why it's called an enlargement. So what happens here is to show the relationship between the original size of your object and whatever's on paper or whatever you're seeing in front of you, there is a scale factor. This scale factor is the ratio between what it is on your diagram over what it is that is the original size itself. So if your image is on top and your original is on the bottom, let's say this is an enlargement, meaning that this big fat mosquito is going to be blown up. The size of it is going to be bigger. If the top is bigger than the bottom, that means you're going to have a larger scale factor, or a scale factor that is greater than 1. So for example, if my mosquito, do I have an example down here? No, it's okay. My mosquito's what? 1 millimeter? I guess 1 millimeter. And then this guy over here is probably 2 centimeters. That's going to be 20 millimeters, okay? So let's say the actual length that you see on paper here is about 20 millimeters. The actual length of mosquito is about, say, 1 millimeter. Then I'm scaling this up by 20 times. That's my scale factor, okay? So 20, which is my copy, divided by my original, is my scale factor, which is 20. So if I have a big number on top, smaller on the bottom, I'm always going to get a value that is greater than 1. So for enlargements, your scale factor will be larger than 1. And you'll notice that when you're doing questions and whatnot, okay? So now, when we do a scaling, we have to make sure that every part of the original scales up to be the correct size in reality. So here we have an example of an F. Okay, so this is the letter F. So when we scale this F up, not only we have to scale the vertical lines the same way we scale the horizontal lines. So here we can do an example. Let's take a look at the vertical line. My original diagram is 2 centimeters. My scale diagram, or the copy that I made, is 5 centimeters. So we take the copy divided by the original, which is 5 divided by 2, that gives us 2.5. 2.5 is our scale factor, which I'm going to abbreviate with SF over here. Then we will check the horizontal lengths of the F. The horizontal length in the original diagram is 1 centimeter. In the copy, it is 2.5. So this is the copy divided by my original. 2.5 divided by 1 gives us 2.5 for our scale factor. So notice, in order for you to have a legit scaling, you need to make sure every dimension of your diagram is scaled the same way. Both the horizontal and the vertical, or actually flip, the horizontal and the vertical are both scaled the same way. Just like in a 2D diagram, like something on your graph. Should be scaled in both the vertical axes and the horizontal axes. So each length orange and down is multiplied by 2.5 to get the matching length. This value is called the scale factor. 2.5 is your scale factor. Notice it is greater than 1, so that the copy of the F is bigger than the original. It's an enlargement. A few more terminology terms to make sure we are clear on everything. First one is this one, corresponding lengths. So corresponding lengths are matching dimensions on your original versus your copy. For example, the corresponding lengths for your original diagram and the scale the copy, this one's a corresponding length. This vertical one versus this vertical part of this F, this is a corresponding length, because notice my 2 to the 5 scales up by 2.5. If I try to scale this vertical with this horizontal, it doesn't work. 2 times 2.5 does not give me 2.5 centimeters. So those are not corresponding lengths. For my horizontal, it would be these guys over here. These are my corresponding lengths over there. So then this is what we just talked about. When the corresponding lengths all scale similarly, then we say that the corresponding lengths are proportional. So 2 to 5 is proportional to 1 to 5. So if I had to represent this mathematically, it would look like this. 2.5 over 1 is exactly the same as 5 over 2. They are proportional to one another. It's a proportional scaling for all dimensions of my f, for my original copy. The one thing that is very important that you have to be careful of is the fact that when you do scale up and scale down, you must be very careful that the units of the lengths must all be the same. Okay? So what that means is if I have, if I'm comparing corresponding lengths, so for example, if I'm comparing the 2 centimeter to the 5 centimeter, I have to make sure that these two both use centimeters. If one is in meters, I'm going to get a completely different number. And that is not going to match the scaling for the top part of the F. So we have to make sure all the units are the same. This is why I keep emphasizing units are super important, okay? So I believe I am going to end the video right there with this first example. So that's the idea of scaling, is you're blowing something up by a certain amount, by a factor of 2.5, 5, and the scale factor for enlargements is always greater than 1. Okay, so hopefully this is you learned something in this video. It all made sense to you. We are going to apply this in more examples in the next video. So thank you for watching. See you next time on Fat Mama Physics, signing out.